All right, guys, MATH6500. You can see I have a couple of things going on. I have some notes already started. Guess what? I started this video and I got interrupted, which seems to be the theme of the recent instructional videos I'm trying to create. But anyway, I have the data set in data error variances. Again, it's available on through the dataset folder on Blackboard. Created the model, looked at the ANOVA so we can get the mean square error. You can see that I saved the residuals, saved the standardized residuals, and let me go back and look at the QQ plot, because that's the purpose of this video. The purpose of the video is to dive into the normal probability plot and actually give you insight on what's actually going on in this plot. Now, so what we have here is we have the theoretical quantiles compared to the sample quantiles. Now, the sample quantiles just come from our sample, right? Hence the name. The theoretical quantiles are actually a kind of an expected measurement if we are drawing from a normal distribution. So more about that in just a second. So, how do all these points, what do they really mean and what are we really comparing? Well, that's the purpose of this video, is to provide that information to you. All right. So, in exploring normal probability plots further, we work with a couple of assumptions. First of all, we work with the expected value of the errors is equal to 0. Mean of the errors, the mean of the residuals is 0. And the standard deviation of the errors is equal to the square root of the mean square error. Now, one of the coolest things that I have seen in stats, I don't know about that. Yeah, okay, it's top 25%, who knows, is a statement, something that was found. I'm not even sure really who found it. But anyway, I wish it had been me, but I'm not smart enough to figure this out. For a normal random variable, so in other words, we're assuming we have a normal random variable. So we're drawing from a normal distribution. A good approximation of the expected value of the kth smallest value in a random sample of n observations is equal to the square root of the mean square error times this function z of a. Now the a part, we take k, and k again is what? It's the rank, so it's the kth smallest value. So in other words, when we find all of our residuals, we're going to have a smallest one, so that will have k equal 1. We're going to have a second smallest. That's going to be k equal 2. We're going to have a largest value. That's going to be k equal n. Okay? So we have k minus 0.375 over n plus 0.25, where z of a is actually the percentile ranking. So in other words, we're going to calculate this a using this. Then z of a will be the percentile ranking of that. Multiply that times the square root of the mean square error, and we get the expected value. So in other words, at the end of the day, once all the smoke clears, we will plot each E sub I, each error, against its expected value, assuming that we have normality. Well, then we'll look at the deviation. So again, we're assuming we have normality. We're calculating these expected values based on what we should get if we have normality. We're comparing the two, and then again, any deviation from that y equal x line means a deviation from, or a departure from, normality. All right, sounds like a kind of a mouthful, but it turns out it's actually a pretty easy exercise. Now, the very first thing that we have to do is we have to rank our residuals. Well, that turns out it's really easy with R. one of the reasons I love R so much, and I can just very creatively call this rank. I can just use the rank function to rank the residuals. Now, what I want to do now is I want to create, let's just call it data 2, and I want to create a new data frame. And I'm going to depart a little bit from the way that I would do this problem if I were just trying to find these theoretical values, because again I'm teaching, so I'm going to include an intermediate step here. So I would create a new data frame. I would still include X and Y, and I would include the residual, and I'm going to include the rank. So I can attach data 2, and I can do head data 2, and you get to see what we get. So in other words, for the first subject who had X equal 27, Y equals 73, they have a residual of 1.42. Well, that would be the 34th rank. I tell you what, let me just go ahead and I hate to clutter things up, but I think this is needed in this case. So when we glance down through the residuals, we can see that the negative 17.49 is the smallest residual. Therefore, it's going to get a rank of 1. Whatever the rank of whichever has rank 2, I don't see it. No, it's here. Oh, here we go. Rank 2 is negative 14.98. And then when there's 55, so it looks like we have a tie, right? Yeah. Looks like these two observations will make sense because they have the same values, 57 and 109, and 57 and 109. We have a tie here for the largest residual, so they get 54 points. They share the 54th and 55th place. Now, the next thing I want to do is I want to create this A that I've referenced. So in the numerator, I will have K, which in K in this case is the rank, and minus 0.375. And then I will divide that by the sample size, which is 55.25. Now, I want to create data, what I call the other data 2. All right, let's just call this data 3. And again, I wouldn't do this, but this is more of a teaching moment. So I want X, Y, I want my residuals, I want my rank, and I want my A. No, I don't want my A's. Let's do something before I do that. So what are the A's here? The A's are this value here, but what we want is the Z of A, which is the percentile ranking. So I want the, let's just call it the percentile for each of these. Now, what I'm doing there is I need the value that has a percentile ranking of 0.601. So what I'm going to take Q norm, and I want A area below 0.1. So that's going to give me the ZA, and then if I'll take the, let's just call it the expected value, I can take the square root of the mean square error, which we found up here, 72.06 times the percentile, right? Yes. Now, let's create a new data frame. So I'll just call it data 3. So what I want here, obviously I want my X, I want my Y, I want my residuals, and I want the EXP. So I attach data 3, and then I want to look at data, let's just do head data 3. All right, so what I get here is I get a comparison of the residual and the expected value of the residual. And any departure, that a large difference indicates that we are losing normality. We have a departure from normality. But you can see as we scan just the first 6, we can see that these values actually turn out to be relatively close. Quite a bit of difference there. But I'll tell you what, let's go back up and I want to include rank there. All right. So I'm thinking that the biggest difference is going to be the ones with the highest and lowest rank. Yeah, okay. So now if I want to create a QQ plot, I can look at the, let's see, I have the theoretical and the residuals. And you can see that what we get is identical to the plot that we get from above where we did the QQ plot. So anyway, I think it's really interesting to see how these, first of all, I'll just be completely transparent. I think seeing this is worth the price of admission. That again, if we know we have a normal random variable, that a good approximation of the expected value of the kth smallest is a random in a random sample of n observations is given by this relationship. I just think that's super cool. Sorry to be so geeky with you, but I just do. Guys, I guess that really concludes the normality part. Something, just kind of a parting thought about normality before we move into examining, constant variance. I think that, and most of the key players, the big players in regression, agree, or maybe I agree with them, I should say. I think normality is the most difficult analysis of all, including linearity, independence, and of course constant variance. Now if we have a large sample size, think 100 or more, probably don't have as great of an issue, but residuals can appear to be normally distributed when they're not, because maybe the wrong model was used, or maybe the error variance isn't constant. So again, parting thought here, always examine normality last. Check off the linearity assumption, check off the independence, and again, I'm going to teach you all this stuff in future videos. Check off the constant variance, and then check normality last. So I guess that's the parting words of wisdom. All right, gang, that's all I got. Take care.